All right, everybody. Hello and welcome to a new webinar series hosted by the Western Lake Erie Basin Advisory Group. This webinar series is designed to provide you with updates from Michigan's Western Lake Erie Basin over the winter time. My name is Allison Bressler, and I'm the program manager for the Western Lake Erie Basin Advisory Group. This community group works collaboratively with State of Michigan's quality of life agencies to inform how the state implements projects aimed at managing and monitoring phosphorus in Michigan's portion of the Western Lake Erie Basin. This group is funded by the Erb Family Foundation, who made this webinar possible. Today, we welcome Dr. Ehsan Ghane, who is an extension specialist and associate professor at Michigan State University. Dr. Ghane has research and extension interests in areas of water quality and agricultural drainage. Dr. Ghane's research goal is to increase the performance and profitability of subsurface drainage systems while reducing their harmful impacts on water quality. He's interested in innovative practices that reduce nutrient loss to surface water and conserve water for crop production. Today, Dr. Ghane will discuss controlled drainage, saturated buffers, and drainage water recycling. During today's presentation, please stay on mute to reduce background noise. And to ask questions as you think of them during the presentation, you can put them into the chat, which you can find in the Zoom toolbar, which should be towards the bottom of your screen. And at the end, Dr. Ghane will address the questions in the chat, and then you'll have an opportunity to unmute yourself and ask a question if you would like to do that. And then at the end, there's going to be a survey that will pop up when you close the Zoom window. And so we ask that you fill out that survey to help Dr. Ghane improve his work and to help us improve the webinar series. And thank you all for attending. And I'm going to stop sharing my screen now and pass it off to Dr. Ghane to share his.
Good afternoon, everyone. Welcome to this webinar. I'm going to be talking about phosphorus, reducing phosphorus. Let's start off by this slide where I'm showing the water components of a subsurface drain field. You've probably seen this from my presentations before, and yep, so these are the dominant nutrient pathways. Is there surface runoff, which is this component here. The particulate phosphorus is mainly the main source of the phosphorus that gets lost from that. There's the drainage discharge here, where it would find its way from the outlet pipe, where you can see here, this is where the drainage discharge would leave, and that's where the soluble phosphorus and the nitrogen would leave. So let's talk a little bit about the system of stack agriculture conservation practice. I'm a proponent of this stacked systems, not just focusing on just one thing, but looking at if we can combine things together. So I got soil health, for reducing phosphorus, and then I got nutrient management, and then I'm going to talk about the water management part of this. And actually, did we want to do the survey, Allison, before I move on further?
Yes. Okay. So a poll should have launched on your Zoom window, and we invite you to answer the first question. All right. So the answers are coming in. And then there's the first question about what your profession is, and then we also have, do you have tile drainage on your farm? And if you are in the other category, if you want to put your profession in the chat, you're welcome to do that. Okay, it looks like most of us have responded. Share results. Okay, so you should be able to see the results now, everybody. in the
Okay, so
call.
that's good. Thank you for answering those questions. Um, so, so the presentation is going to be oriented towards more policy making, informing decision making too. So as we move on, so I talked a little bit about this system of stack conservation practices that I can see here: soil health, nutrient management, water management. I'm going to go over each one: soil health, nutrient management, water management, in the next slide, and talk a little bit about each one, just to summarize really what's out there in the literature and also what's happening here in our research lab. Okay, so as I mentioned, the first box was the soil health, that first component. This is what's useful for improving the water quality of surface runoff because it helps improve infiltration and all of that good stuff. And these are the main pillars of this soil health: minimum no soil disturbance, cover crops, diversified crop rotations. But really the message here I wanted to mention here is that research has shown that um, we need the soil health for its benefit that it provides, but soil health alone, if it's just targeted and if it's just soil health that we're focusing on, it's not going to achieve our water quality goals in the Western Lake Erie Basin. And of course, because um, I won't get into too much details, but the soil health reduces the surface runoff um, part of the water pathways, the nutrient pathways that I showed you in the previous slide. And we know that surface runoff is not the dominant source of phosphorus into Lake Erie. We know that drainage discharge is the dominant source. And also there's increased risk. So this is a photo of a macropore from a site with no till. You can see the smoke coming out of the cracks. So there's discussions, lots of discussion that we can make about this. But if this is the only thing that we can focus on and we do the only soil health, this will not achieve our water quality goal. So let's see, what about nutrient management? So in nutrient management, our colleague and with ARS, Dr. Osterholz and their colleagues, they just published this recently and they found that legacy P. So what is legacy P? Legacy P is the phosphorus that's in the soil that has been accumulated there from previous applications. So for example, if you apply, let's say manure on October 1st and you see some of the manure leave, that is not legacy P. That is just the phosphorus that comes from that manure application. So they found that the legacy P was responsible for over 83% of phosphorus loss in Northwest Ohio in the Western Lake Erie Basin. We also replicated this statistical methodology here at our sites, the Clayton and the Blissfield site in the Western Lake Erie Basin in the River Raisin watershed, and we found over 80%. We found similar results. So legacy P is dominant source of phosphorus loss. And recently, just recently, another publication came out by Gattiboni et al. 2025. They showed very interesting results. They showed that reducing the soil test phosphorus by not applying phosphorus fertilizer. So what they did a meta-analysis, and if they don't apply fertilizer, they found that if you want to reduce the soil test phosphorus, that's going to be a very slow process to reduce the P loss here, especially if you have fields with higher soil test phosphorus, because the fields that had higher soil test phosphorus, they were even slower for reducing it. So this is some of the results. So they found that fields with the higher soil test phosphorus have a slower rate of drawdown, and they calculated about 4% reduction per year. That's pretty slow. So you're looking at, if you had 100 parts per million STP, soil test phosphorus, you'll be looking at reducing just 4, going to 96 after 1 year, and then another one, 92. That's going to take a long time. Oh, another way they described this slow process was that the soil test phosphorus reduced to half of its initial soil test phosphorus over 16 years in fields with high STP. And these fields with high STPs, soil test phosphorus, were the fields that had about 100, 110 and over soil test phosphorus. So really, what I want to show you here is that the first point here that I mentioned, the legacy P, so the legacy P is related to the soil test phosphorus, of course, and reducing it. And if we could find a way to not apply phosphorus fertilizer in the watershed, if we could, it would be a very slow process. And that's also shown by another research, high quality research, Simpson et al., 2024. These are all recent publications, by the way. So it shows that soils across, they did a meta-analysis for the soils across the USA, and they found that there's enough legacy P to sustain high and severe, these two words are from their own publications, high and severe P loss for decades. Just like I showed you here, when I mentioned that it's going to take over 16 years with high soil test phosphorus, it is a very slow process. If we were only working on reducing this soil test phosphorus in a nutrient management setting. So really the message here is that, one, we got to target fields with high soil test phosphorus. We already probably know this. Target fields with high soil test phosphorus. And two, nutrient management is an excellent good start to reduce phosphorus going to Lake Erie, but on its own, it's insufficient to achieve our water quality goals in the short term. It's going to take a very long time. Research shows that. So what do we do? I mean, if soil health is not going to help us for this goal, soil health has other applications that are useful. Nutrient management is going to be very slow. So is there a way to get to our goal in the short term? We're going to talk about that. So in the later slide. So let me show you how the phosphorus moves, because I have another message here. So in the previous slide, one of the messages was that we got to target field with high STPs. And even if we target those fields with high STPs to lower those, it's going to be a very slow process. We got to recognize that. So let's look at some data from our site. So this is time. You can see I got 19th of March, 24th and 29. And then here I got drainage discharge in inches per hour. So this is going to be the rate of water leaving the field. And then on this side, I have hourly phosphorus concentration in milligram per liter. So let me show you the hydrology. So this is how water moved. It responds to rainfall. Then I'm going to show you the phosphorus concentration. You can see how it's moving here. I call it like a roller coaster that phosphorus riding on, because it goes up fast, comes down. It's like a sprinting, going up, down, really quick, like a roller coaster, very fast with rapid changes. So what really here, the message here is, the previous message was target fields with high soil test phosphorus. Even if you target those, reducing those with nutrient management alone is going to be a very slow process. Here, the message is that we got to target those events. So if we find those fields with high soil test phosphorus, our attention should be focused on those sections that have high those areas that have event flows, basically. So we're targeting the event flows, because here you can see we calculated the event flows being responsible for about 90% of the phosphorus loss. So put those two layers together. The legacy P is a dominant source of phosphorus loss. And it's, so I can connect legacy P to this slide too, so you can get a better idea. So these phosphorus concentrations going up are not because there was a fertilizer applied here or here right before. This happens every time when there's an event. And this confirms what the other research shows. And we also have done that about over 80% of this loss is because of legacy. So if we were to find a way to stop fertilizer application here, we would do only a little bit. We would do only the 20% reduction over the long term. So 80%, which is the dominant phosphorus loss, will still happen even if we were to stop phosphorus. So that's the point I want to emphasize again here. That's very important. So when we get to those fields with high soil test phosphorus, we got to find a way to target these high events, and we can do that with water management, these higher events, because they're dominant, 89%. So let's go back to that again. So I talked a little bit about soil health. It has multiple benefits, but for reducing phosphorus loss, it's just not going to, alone, it will not be enough. Then I talked a little bit about nutrient management. I said that research shows that it is a very slow process to lower that soil test P. And alone, it's going to be insufficient for the short term. It's going to take decades to get results if we just do the nutrient management alone. And then there's water management. So does this work? Can we get something out of water management over the short term? So let's look at it, control drainage. So I'm going to jump into the results. So I have a scale here, the outcome. This is the sad face, this is the happy face on the right side. And on this side, I have basically increased DRP, dissolved reactive phosphorus, concentration in drainage discharge. That was an outcome of the control drainage part of the project here. And you can see a photo of control drainage on the left. And on the right side, I have basically reduced drainage discharge, which is an outcome of control drainage. We can reduce the amount of flow that is leaving the field. And then on the top, I have DRP load in drainage discharge, which actually sits on the right side. And it, basically the scale is level, meaning that it's not tipping in either direction. So this is what we found after 4 years of data collection. We have 1 more year to go. So we really haven't seen anything outcome out of that. So let me show you a little bit more detail of that. So the scale on the y-axis here is percent reduction of the drainage usage and the phosphorus load. These are the water years, 21, 2, 3, 4, and also the combined, all of it together. So first, you can see the drainage discharge. You can clearly see, as I mentioned, control drainage reduces drainage discharge. So it's very effective for nitrate load reduction, which is the focus in the Mississippi River Basin. Here, we want to work on phosphorus because we're surrounded by freshwater bodies. So let's look at the phosphorus, here what it looks like. So you can see 1 year, 2021, it actually became a source. 2022, it was pretty good. 2023 was better than 2024. It wasn't as so good. What was happening here is that, like I mentioned in the previous slide, when we implement the control drainage, phosphorus concentration also goes up. So it really becomes, you got two sides of this scale, fighting over who's going to win. You got increased phosphorus concentration and you got reduced drainage discharge. So whichever one is strongest is going to tip the balance. So in this case, really, the balance was that it really eventually ended up with just not doing much. We have 1 more year to go, so it really depends on basically the weather. Is it going to be similar to 2023? If it does, then this is going to become positive, or is it going to be like 2024? So we will see. But really the message here is, I want to mention is that that's why is that we really push the control drainage to its limit. Here it is, pushed its limit here, because we had 10 months per year average of raised outlet elevation. And it is really, really pushing it to its limit. The research coming from Ohio had about 6 months per year of raised outlet elevation, which also they didn't find any benefits of controlled drainage for phosphorus load reduction. But we push it to its limit, and it will be very hard or impossible to just push this to 12 months. We can't do that. And I explained the reason here in this slide, where I got a control structure here, and I'm going to slide in one of those weirs here, and then I'm going to show you how water flows over this. So then I'm going to show you a snapshot in time from October to September. This is our recent data, and this is the water level inside that structure. This is the precipitation pattern over time, and this solid black line is the ground surface where I have two crops growing here to demonstrate that. So this line here is the weir elevation of the free drainage. So basically this is free drainage, conventional, and this is how water level changes. Basically, whenever water level is above it, you can see here in this corner here, water will flow. It's free drainage, so it's just flowing freely. But this is the one that was controlled drainage, and I showed you the data for that. And this is the water level inside the controlled drainage structure. You see how it's like a step higher. But when we get to those months that we really need to open the system, because we need to have the field provide trafficability. We can't just continue this dashed line here, go all the way down here, just connect this, because the field would just be too wet for planting in springtime. So we really need to open it up. And that's where we lose some of the phosphorus as well. So we're really pushing the limit of control gene to its limits in terms of its time management and also in terms of its weir management depth as well. So because we're working with the conservation district, so we really focus on this. These weir elevations are pretty, really to its limit. We can't really, it would be hard to push it even closer to the ground surface. And yet we see, small changes, and the concentration increase is kind of, in some years, it's winning the battle against that flow reduction in some years. So really, what's next? Now that we know, control drainage does good in reducing energy discharge, concentration goes up, and it's really so variable, depends on the year. So really, this is the water management practice that I wanted to talk about. There's another one I'm talking about it's next up, would be the drainage water recycling. So let me talk about this one as well. So this is the drainage water recycling. This is, in my opinion, this would be a solution to the phosphorus loss and the too much rain or too little rain. One thing we need to focus on is that when I talk with the extension, when I talk to the farmers, well, often they say we care about the water quality. We want to reduce phosphorus loss, but also they ask about, how can this affect my bottom line? What is the economics? So these things come into play, and with controlled drainage, it becomes difficult because the yield benefits with controlled drainage alone, as I talked about previously, it's just so variable. Depends on the year. Some years doesn't show much, and it is really it's not a strong case to be made there. But when we get to drainage water recycling, this too much rain and too little rain would be addressed. So the too much rain hurts the crops, right? So if you get too much rain, it's going to drown the crops. And then when you don't get enough rain, if you get too little rain, that's a problem. So I hear that a lot from farmers, that either too much rain is a problem or too little rain. And then phosphorus, of course, that's the topic we're talking about here. So there is an NRCS standard 447 for this drainage water recycling. And in the South, they call it tailwater recovery. We're calling it drainage water recycling in the Midwest. Basically, we capture the water, we store and reuse. So going back, remember I mentioned that these few months here, we're pushing it to its limits, and there's some nutrients leaving here during these months that we must lower that elevation for free drainage. So if only there was a way to capture this water, and there is, that's why I'm mentioning this slide after that. It's drainage water recycling, because that's where we can capture those months, store them, and reuse them. When you reuse those waters, then we would be addressing the too little water. And going back to the point about economics, let me explain the increases. So this system also increases drainage intensity, meaning that it will have faster water removal because of the narrower drain spacing requirement of this system. And also in terms of this corn yield, because we can store and reuse water for irrigation later, Research has shown that it can increase corn yield by 61% and soybean by 31%. Canada, Ohio, North Carolina, Missouri, and Minnesota have done work in the crop yield. We have not in Michigan. Of course, they found that it reduces year-to-year yield variability, which is another important part of that. So which really dampens the effect of too much rain or too little rain. It kind of, because you have that store of water, you don't have to worry about the too little rain, and also reduces regulatory burdens associated with groundwater withdrawals. We can't have like every grower have a pump, groundwater pumping. There is, of course, there's regulation on that. So this would help with that because now you got a source of water that could also be added to groundwater pumping if that's available. So both, I have seen systems in Michigan that have both, and I have seen systems that I have only this system where you just capture and store and reuse. One study in North Carolina showed that it is effective in reducing phosphorus loss because you're storing that water. And as I showed you in that previous graph, this would be the water that, for example, for that period of time that it's going on the fridge, we would be storing. Because really, if you see the heading, it's drainage water recycling with controlled drainage and an irrigation system. So it's a system of stacked water management really here. So summing up the water management, I talked a little bit controlled drainage. Controlled drainage has potential. We need to look at controlled drainage and its stacked effect with nutrient management. We really don't know how that is. We have looked at controlled drainage alone. And then there's drainage water recycling, which I strongly believe that this is the way to go. The force is the strongest with drainage water recycling. It has multiple benefits. And as an investment, it does pay back. So we did some really basic payback for a site in the River Raisin watershed, and we found about 10 years payback period for the drainage water recycling in that system in Southeast Michigan. So to wrap up my slides, so the take-home message is we need system of stack practices. We need to have soil health, it's important. We need to have nutrient management, that's important, but there's limitation to these. I mentioned that the nutrient management is going to be a slow, very slow process to reduce the soil test phosphorus. Research shows that. We need the water management. I showed control drainage is good, but alone, it may not be strong enough. The force may not be strong enough with control drainage. But we don't know how control drainage would affect phosphorus loss if it's combined with nutrient management. So we really don't know that. We need some answers on that. And also the drainage water recycling with controlled drainage and irrigation, that has numerous benefits. The economics, there are some preliminary data for the economics, but we need more to show the benefits. And the difference would be that a system that helps protect the crop and improve crop yield, that one would have its own incentive for people to actually adopt it rather than just focusing only on having a water quality alone benefit. But because this renewable recycling helps the crop, I see a lot of potential here. And other states have research going on, like I showed you some of the names of the states. Ohio is moving ahead with research. We don't have research with that drainage water recycling system here in Michigan. And just one slide, I want to put one slide, last slide about two-stage ditches. Ohio has done work on this, Minnesota has done some work on this, and I see a lot of benefit in that too, which we don't talk about here often. We don't talk about this. So it's this two-stage ditch is basically you got your conventional ditch, but in the two stages you have a main channel and then you got your floodplain here. And this slows down water, it reduces flood peak, it reduces erosion, it reduces phosphorus loss. You got less bank slumping, which is when the edges of the banks, come back in and because of the erosion. And then you got less ditch cleaning. So this is another part of it that is important. If you have less ditch cleaning, you pay less taxes. So that's important. And also it it lets the pipe flow better out because one thing not rarely heard people talk about that. It's actually visible in the diagram. So let's say you got the water level here and the ditch floods. We see that often in our sites. If this comes up, this outlet is going to be impeded and it's not going to be able to flow freely as easily. But in a two-stage ditch, you're giving that because water moves in the main channel, you got the floodplain, so the water can spread out on the left and right side in the floodplain. So there's more free flowing and the better drainage, which we really don't talk about. That is a benefit here. So thank you so much for